Hello everyone. So we are going to continue with coordination compounds and today is our lecture 31, second lecture of coordination compounds. So last class we have discussed about different type of compounds, ionic compounds, covalent compounds, then addition compounds which is divided into two, that is double salts and coordination compounds, then the difference between the double salts and coordination compounds, then some of the basic terminology related with coordination compounds like ligands, classification of ligands, after that coordination number, coordination entity, coordination sphere, then how to find out the oxidation state of central atom, homolyptic and heterolyptic complexes. So these are the things which we could complete in our last class, and today I am going to start with IUPAC nomenclature and formulation. So first of all, how do we write the formula of a coordination compounds, and after that we'll discuss the rules for writing the IUPAC names. So far as IUPAC formulation is concerned, while writing the formula of a coordination compound inside the coordination sphere, first of all we write the central atom. After that we write the ligands. Whatever ligands are present, if only one ligand is there, well and good. If more than one ligands are there, then they have to be arranged in an alphabetical order. But if the defining atom is same, suppose ammonia is present and NO2 is present. So both the cases nitrogen is the first atom or the first alphabet, then how we are going to assess and assign that which is to be cited first? So if such a case arises, then we would consider the next atom. So in case of ammonia, after nitrogen, hydrogen is there, but in case of NO2, oxygen is there. So therefore ammonia should be cited first, followed by NO2. Now the counter ions, suppose Cl2 is there, sulfate is there and so on, that should be written outside the bracket, outside the coordination sphere. If complex ligands are present, suppose pyridine is there, then ethylene diamine is there, so in that case these complex ligands, they have to be represented in small parentheses, that is small brackets. If any cation is present in the complex, that should be cited at first. Suppose potassium ferrocyanide. So in this case what happens? First of all we write cation, then the central metal atom, followed by ligands, and the complex ligands, they have to be represented and written in parentheses. Okay, and alphabetical order, that is a must to follow while writing the name of or formula of a coordination compounds. Okay, now we are going to start with IUPAC nomenclature. Okay, so far as IUPAC nomenclature is concerned, just like organic compounds, here also some specific rules are there. Okay, now rule number 1 says that formula of a cation is to be written first, followed by anion, and likewise the names also. This is a universal rule, my dear students. Sodium chloride, potassium nitrate, ammonium carbonate. So always we name the cation first, followed by anion. So cation should be named first, followed by anion. Okay. Then in the coordination sphere, the ligands are to be named first, followed by central atom, which is just reverse as compared to formulation. Make a point of it. That's very, very important, because when we write formula, then we write central atom first, followed by ligands. But while naming them, the ligands are to be named first, followed by the central metal atom. Okay, so suppose here CrNH3 whole 6 Cl3 is there. So ammonia is the ligand, so ammonia would be named first, then central metal atom, and then the counter ion is to be named. Now, if more than one ligands of same type, similar type, then the prefix di, tri, tetra, etc. will be used, like dicyanide, trihydroxo, disulfato, and so on. And if in the ligands itself di-tri is attached, suppose ethane 1,2-diamine, in that case triphenylphosphine. So if di-tri is attached in the name of ligand itself, then what we are going to do for such ligands, complex ligands, then we have to use bis for 2, tris for 3, tetrakis for 4, and so on. But this is to be applied provided the ligands are complex. Now, the negative ligands, the name ends with O. Fluorido, chlorido, bromido, iodido, thiocyanato, sulfato, carbonato, oxalato, dimethylglyoxymato, and so on. For positive ligands, the suffix is ium. Nitrosonium, nitronium, NH4 plus will be ammonium, NH2, NH3 plus, hydrazinium, and so on. But for neutral ligands, no characteristic ending. It would remain as such. But there are some specific ones like CO. It would be named as carbonyl. NO. It will be named as nitrosyl. H2O. It is named as aqua. NH3. It is named as amine. And just see in amine there would be double M. Make note of it. Okay. So for organic compounds, when we write amine, diamine, triamine, that time single M is there. But for ammonia, in coordination compounds, since we are writing their IUPAC names, we have to be specific even if we are going to use their spellings. Okay. So in case of ammonia, it is named as amine. So far as others are concerned, like PH3, it would be phosphine. But if it is triphenylphosphine, then in this case, here there is no change at all. It would remain as triphenylphosphine. And one more thing, all these neutral ligands, ethane 1,2-diamine, aqua, amine, carbonyl, nitrosyl, phosphine, triphenylphosphine, pyridine, all these cases, their oxidation number will be 0. They are neutral. So their oxidation state is 0. So once again, now the next rule. So let us repeat once again. So first of all, cation, then anion. Central metal atom should be named afterwards. First of all, ligands, then metal atom, then the counter ion. The name of negative ligands ends with O. Positive EM and neutral as such. For more than one ligands of similar type, di, tri, tetra. For complex ligands, bis, tris, etc. we are going to use. Then, if the complex is negative, okay, suppose FeCN6 minus. If the complex is negative, then the name of the central metal atom ends with 8, ATE suffix, ferrate, cobaltate, nickelate, pallidate, chromate, etc. But if the complex is positive or neutral, then no characteristic ending. Am I clear? And so far as the oxidation states are concerned, oxidation state of the central atom should be written at last in Roman numeral just before the counter ion, if any. If there is no counter ion, then the oxidation state would be written at last in Roman numeral. So these are the certain specific rules for writing the IUPAC names of coordination compounds. So let's begin with IUPAC nomenclature. Okay. So very simple example, as you all know, K4 FeCN6. Potassium ferrocyanide is its common name. So as I said that first of all the cation should be named. So potassium, whether it is 1, 2, 3, it is immaterial, dear students. Okay. So either it is K1, K2, K3, K4. We are going to write potassium. Similarly, if it is sodium, whichever metal is there, you are going to write only the metal, that is potassium. Inside the bracket, now ligands are to be named first. Since 6 cyanides are there, so what we write here? Hexacyanido. Okay. Since it will ionize as 4K plus FeCN6 4 minus. No need to show it, but for your own understanding, you can dissociate and see that whether negative ions are formed, complex is negative or positive. So charge is negative, that means the complex is negative. So what we are going to do is potassium hexacyanido ferrate. Why ferrate? Because the complex is negative. And at last, oxidation state. How come it is 2? Because potassium is +1, so this is +4. Cyanide is -1. So 4 plus X plus 6 into -1 is equal to 0. So therefore it is potassium hexacyanido ferrate 2. Similarly, AgCN2. Okay. So in this case you see X plus 2 into -1 is equal to, suppose here minus charge is there. So this is equal to -1. So X minus 2 is equal to -1. So silver will be in +1 oxidation state. So this will be dicyanido argentate 1. Why argentate? Because the complex is negative. If it would have been positive or neutral, then it would remain as silver. But Latin we are going to use if the complex is negative. Now, Cr NH3 whole 6 Cl3. Okay. Now you see here X plus 6 into 0 plus 3 into -1 is equal to 0. Then chromium becomes +3. So how we are going to name this compound? Here no cation is there at the beginning. Directly we are going to approach ligands first. Hexaamine. Hexa because 6 ammonia in amine, double M should be there. Hexaamine chromium 3 chloride. Okay. Hexaamine chromium 3 chloride. Okay. So after the oxidation state, then the counter ion should be written. And same thing here also, whether 1, 2 or 3 ions are there, we are not going to represent the number of ions, rather we are going to write only the counter ion, chloride, bromide, sulfate, nitrate, whosoever is present outside the bracket. Now some more examples you see. I hope everybody remembers this compound K2HgI4. For ammonium ion, we use this during qualitative analysis. This is Nestler's reagent, commercial name. How to name it? So this is +2 and here -4. So mercury will become +2. So how to name it? Potassium tetraiodido mercurate 2. Why does it become mercurate? Because the cation is there, so naturally the complex is going to have a negative charge. I repeat, potassium tetraiodido mercurate 2. Some more example. Now you can see sulfate is -2, copper becomes +2, ammonia will be 0. So this is tetraamine copper 2 sulfate. Tetraamine copper 2 sulfate. Why copper? Why not cuprate? Because sulfate, this counter ion is negative, so the complex will have a positive charge. Okay. potassium tetrahydroxo zincate 2. Once again, this is -4, this is +2, so zinc will be +2. Why zincate? Because the complex is negative and the potassium is having a positive charge. So I repeat, potassium tetrahydroxo zincate 2. Now see some neutral coordination compounds, NiCO whole 4. So in this case, nickel will be 0 because x plus 4 into 0 is equal to 0. So how to name it? Tetracarbonyl nickel 0. I repeat, tetracarbonyl nickel 0. Similarly, Pt Py whole 4. Py stands for pyridine. Tetrapyridine platinum 0. Tetrapyridine platinum 0. We'll see some more examples. I hope it's clear to everyone. Cu Cl4 2 minus, Ni CN4 2 minus, oxidation state here also +2, nickel also +2. Tetrachlorido cuprate 2. Why tetrachlorido? Because 4 chloride ions are there. Why it is cuprate? Why not copper? Because you can see the complex is having 2 minus charge. Likewise, tetracyanido nickelate 2. Tetracyanido nickelate 2. FeEn whole twice 2 plus. Okay. Now you see here ethane 1, 2 diamine. That's the ligand. So we cannot say diethane 1, 2 diamine. So now we are going to use bis here. So how to name it? First of all, we would start with bis. Then in bracket, ethane 1, 2 diamine. Close the bracket. Iron 2. Okay. So why it is iron 2? Because the complex is positive. Oxidation state x plus 2 into 0 is equal to +2. So naturally iron is going to be +2. So bis we have used because the ligand is complex here. Similarly, Fe C2O4 whole thrice 3 minus. So here we have used iron, but in this case we are going to use ferrate. Why? Because the complex is having a negative charge. So x plus 3 into -2, oxalate is having -2 charge, -3. So this becomes x minus 6 is equal to -3. So +3. So how do we name it? Trioxalato, although it's a bidentate ligand, but since the ligand does not have ditri, so we can use ditri over here. Trioxalato ferrate 3. I repeat, trioxalato ferrate 3. Now, if two coordination sphere is there, suppose Cr NH3 whole 6 and Cr CN6. Okay. So in this case, what happens, my dear students, when there are two coordination spheres, in continuation we are going to name them. And one thing remember, that metal has to be in its common oxidation state. Apart from that, it has to be in its positive oxidation state. So far as chromium is concerned, as you all know, +3 common oxidation state is there, especially while forming the coordination compounds. And ammonia being 0, if we make here 3 plus, then chromium will become +3. X plus 6 into 0 is equal to +3. Likewise, x plus 6 into -1 is equal to, if we make here -3, then also chromium becomes +3. But how to name the compound? Hexaimine chromium 3 hexacyanidochromate 3. I repeat, hexaimine chromium 3 hexacyanidochromate 3. This completes the name of this coordination compound, which has got 2 coordination spheres. Okay, so you have to name it in such a way so that there is no gap. At the same time, the metals, they are in their positive oxidation state as well. See one more example. AgNH3 whole twice and then AgCN2. Okay, and as you all know, silver normally it shows its +1 oxidation state. So here if I make plus and here if I make minus, in both the cases silver will be in its +1 oxidation state. Okay, how to name it? Diamine silver 1 dicyanidoargentate 1. Here argentate because the complex is negative. Here it would remain as silver because the complex is positive. Okay, so diamine silver 1 dicyanidoargentate 1. This is the way we are going to write the IUPAC name of a coordination compound having 2 coordination spheres. Okay, my dear students. So plenty of examples are given in NCERT in text and exercise. Okay, question number 1, 2, how to write the formula and write the IUPAC names of the following. And in text also, solved examples are there and then unsolved examples are there. Practice well so that you have a proper command over writing the IUPAC nomenclature of compounds. And the valency also, like DMG, dimethyl glyoxymato, it has got -1. Thiosulfato, it has, thiosulfate is, what the formula of thiosulfate? SCN. It has also -1 valency. Then silicate SiO3 2 minus, tetrathionate S4O6 2 minus, NO2 if nitrogen is the donor atom, nitrito N. If ONO, then it would become nitrito O, and so on. So practice well. This is very, very important topic of coordination compounds. Okay, so only here it's not very complicated. Like organic chemistry, what happens? There are so many rules, but here only certain specific rules are there and there is no deviation, no violation from the general specific rules. So once you go through the rules and practice some of the examples on your own, I am sure you are going to have a proper command over this. So thank you all. Thank you very much. We are going to meet in our lecture 3 of coordination compounds very soon. Once again, goodbye. Thank you.